Before we get to the binomial theorem, we want a quick and easy way for computing some of the values for Pascal for the binomial coefficients. So we're going to talk about a device that we can use known as Pascal's triangle. Pascal's triangle. First, in the last video, I mentioned how to use your calculator. The actual approach, again, formula-wise, is this: that if we have a binomial coefficient, p choose k, then on your calculator, depending on your calculator, it'll either produce it as NCR parentheses, and then you type in p comma k, or it may type it in as with blanks with the C in between them, and you fill them in like you did on my calculator. And again, you get to that by going on your calculator, TI-83, TI-84 type calculator, to math, probability, and then NCR. Math, probability, and then NCR. Okay, so back to Pascal's triangle. You've probably seen this before. This triangle that's generated by having 1 in the first row, and then 1 in your second row, and then continuing now 1, 2, 1, and then row 3, 1, 3, 3, 1. You've probably seen this before. And if we continue, we would have 1, 4, 6, 4, 1, and then let's do one more row, 1 or 2 more rows here. 1, 5, 10, 10, 5, 1, and then one final one here. 1, 6, 15, 20, 15, 6, and 1. Whereas you're going down each diagonal here, the next number here, so this 2 is the result of 1 plus 1. And of course we assume that there's a whole bunch of zeros outside here as well. So this one is 0 plus 1. This one is 0 plus 1. This one is 0 plus 1 there. And so, and then the internal ones you can see, 1 plus 2 gives you 3. 2 plus 1 gives you 3. And you have this additive nature. 4 comes from 3 plus 1. 6 comes from 3 plus 3. Right? You have this additive nature of defining the Pascal's triangle, where this is your k row, and they're starting as k equals 0, 1, 2, 3, 4, 5, 6 coming down. And then your rows are row 1, 2, 3, all the way down to 6 here as well. So we would read this as 6C1 would be right here. In row 6, column 0. Sorry, 6C0. Said that wrong. 6C0. Right? 6C0 would be right here. In the 0th diagonal in the 6th row. 6 choose 1 would be right here. 6C1, or in our notation, 6, 1 would be right here. 6, 2, 6th row, 2nd diagonal, right here. And so on across the line until you get out here where you have this last entry, which would be in the 6th diagonal, be 6, select 6 things. So this is called Pascal's triangle. And we're going to use this, and you can actually go back, and if we have any of my results. Actually, I think I do have one result up above. We had 5, choose 3. So if I went to my 5th row, that would be this row right here. We've had 5, choose 3 earlier. We saw that 5, choose 3 was 10. So if we go to our Pascal's triangle, 5th row, again this row right here, we need our 3rd diagonal. The first one's 0, so 0, 1, 2, 3. So here we are in the 3rd diagonal. 3rd diagonal, 5th row. You see 5, choose 3 is 10. Now we also did 7, choose 2. I don't have the 7th row written down, but if I did, that would be 1, 7, 6, and 15 is 21. Now that'd be your 7th row, and second diagonal. There you are. 7 choose 2, and if you go back to our result, 7 choose 2 is 21. So for small values, Pascal's triangle is nice because you can just look at it and read off the solution for the binomial coefficient. When you get to some bigger numbers, then you're probably better just computing them. So that's Pascal's triangle. And I wanted to go over that because we're going to use it in an upcoming example here where we want to talk about the binomial theorem and use it as an example without having to compute every one of these by using our formula up above, which, on its own can sometimes definitely be a little tedious. Okay, so that's Pascal's triangle, and maybe you've studied that before and used that to raise things to powers in the past. But we're going to see in a moment how we could use that just to raise a binomial up to some positive integer power.